on this computer. If somebody can hit the lights back there, that'd be awesome. So that's not completely dark in here. So this will take a bit of time to set up. Currently, I'm loading up so for those of you who don't know, on, or we can have them on, off. It doesn't really matter. I don't think it affects too much over here, so we'll see. Just having the front one on makes the glare horrible. This will take a bit of time to load due to the fact that, yeah, stop converting. So that due to the fact that music projects are quite large. Now, first off, for those of you who don't know, I have a hobby where I like to do orchestral music, remix music from video games, write original compositions, and use also machine learning to basically create new pieces of music or add on additional parts to music. Nothing that fancy today. I'm just loading up something that I like the sound of from a video game, and I'm loading it up now. So part of the reason it takes so long to load is because music samples are large, and music software is large, and music programs are large. We're talking, the fact, look, my main computer at home has like 48 gigabytes of RAM, and that's for a reason. Because it's not for gaming. I love gaming, but gaming don't need that much, fortunately. But actual production does. So what we're seeing here is what's called a DAW, or a digital audio workstation. Okay, and now a digital audio workstation is, and the reason we're doing this is because it's the easiest way I can demonstrate today's topic. So sound, let's see. Oh, excellent. So easiest way to demonstrate today's topic, which is compression, which is really important in today's society because of all the media we share, be it on social media, via video, via GIFs, via music. Anything we share basically has to go through compression. So like, here's a piece of music that I've been working on that I've been remixing. It's made by somebody else. It's from a 2000s remake of a 1990s video game for the original Game Boy. So give me 1 second, and let's just take a listen, because, and I promise I'm not just like showing off because, oh, this is my hobby. So what's cool about this is that like a lot of this is being done with different kinds of virtual instruments. Like this horn part is completely virtualized. It's made off of real samples, but a lot of clever programming is going on to make it sound really realistic. Specifically, these are basically these lines are the velocity, how hard somebody hits the keyboard, and that affects basically how hard the initial attack is of the note, or the speed of a legato slur, which is when two notes are connected. And this is the overall breath, essentially, that is being simulated. This is one approach to doing an instrument, which is basically to model the instrument somehow. Another approach is what's called sampling. Now, all these strings are sampled. This is an entire string section that has been sampled from that. This was recorded by, this is a record, basically. So what we've got here is basically a recording of the BBC Symphony Orchestra. that's been recorded note by note at different dynamic layers, different techniques of playing, and basically programmed in. This is another way of doing it. Okay. And it sounds pretty realistic, I would say. Part of that's because it's recorded in, you know, their actual playing location, because you can hear that like that diminishing echo, that reverb of the natural reverberation of the room. So doing modeling is fairly cheap. This basically instrument doesn't really take up too much RAM. It uses maybe, yeah, it's using 25 gigabytes of RAM. But all these strings together that I have loaded up, these strings I'm using with the strings and like the flute and clarinet and glockenspiel and triangle and other stuff, I'm using 4 gigabytes of RAM. And this is because sampling, well, which gives you very realistic results, is also very expensive. The entire library is about, the version I have installed on my laptop, which is the one I can install on my laptop, is about 28 gigabytes of compressed audio. The actual like full sample library that I also own is about a terabyte. Sorry, is about a terabyte uncompressed, maybe, and about 600 gigabytes compressed. That's a huge savings with compression. But here's the thing with compression, okay? There's 2 ways of doing it, which is why I booted up this music, because we'll be able to see there's 2 types of compression. There's lossy and there's lossless. So we're going to go ahead and see what lossy compression is like. I'm going to go ahead and just record. I'm going to render this short loop over here, this part. Okay. So what I'm going to do now is I'm going to render it, which means basically save it in a file. Okay, export mixdown. And there's different file options here depending on it. So first thing we'll do is that we will go ahead and I will render it as a wave file, and I'm going to say wave output, just as the name. This is basically the raw recording of it, completely uncompressed, and it's just this 17-minute marker or 17-second marker. So shouldn't take too long. It renders it at twice what normally real time was, and sometimes I need to do it twice because because these instruments can be weird. So let's go ahead and see. So the wave output was about 3.2 megabytes. But now let's go ahead and take a look at MP3 format. So MP3 format is what we call which is one of the oldest kind of music formats there is what's called a lossy format. And the way it works is that your human is basically what is being recorded in a wave file is a sound is basically the sound wave. Just basically think of points, yeah, wave file. Let's go ahead and take a look at it. So file format, old file format, and what it stores is various just kind of what it stores is basically just a sound wave, something like this, some kind of waveform, which looks like it's blocky, but it's actually like a, you know, a parabolic line going up and down, you know, in a sinusoidal pattern. And that's what causes the vibration in your eardrum and produces noise. Right? It looks something more like this. Okay. So, and we need to save that in some format, but basically the data that is saved in a wave file, the human brain doesn't necessarily need all that information. So if I like throw out a bit of it, it's not going to affect the overall sound. And then I can make the file much smaller. Okay. So here I'm basically saying, hey, I want to dedicate 192 kilobits every second that this is, for every single second of this that this goes on. So that means that basically so 192 times 17.1 is basically going to be the size of this output file. Okay. Okay, so the size of this is 400 kilobytes. Now, that is versus 32 kilobytes. Sorry, versus which is 300 meg. So 3 megabytes versus 400 kilobytes. That's a huge difference in between MP3 and 400 versus 300 megabytes. That's a big difference. And still sounds great. There might be somebody with quote unquote golden ears who can tell the difference, but I certainly can't. But once we lower it down to a low rendering, 64 kilobytes, which was pretty common back in the day to save space, because space was very limited, 20 years ago. Just like how sometimes the video resolution on YouTube goes down to 144p, 44p in an area you don't get good reception at. This is 4 times smaller. And you can kind of hear it's got this weird tinny quality with the drums now. Still the same song, obviously, just sounds degraded somehow. And that's because it's gotten to a point where our ears can tell the difference between what we've thrown out and what we've lost. Now, this is fun, but for most, media, this is fine. Again, this goes back to our, movies and stuff. Let's see, computer file compression. I think there was not this video, but was it Tom Scott? He did a video on why snow and confetti ruin YouTube video quality. And it's all about the way that compression algorithm works, which is very good over here.
Have you ever noticed that video?
And basically, though, I'm just going to go ahead and just kind of lower the quality from 1080p to 144p. And you notice that it is.
Have you ever noticed that video of falling snow or confetti can look
really janky, right? Kind of terrible looking. But that comes as a cost, but that comes at a benefit. There's a benefit for it to looking janky. The video size is so much smaller, right? It uses up less data. And if it uses up less data, it can get to your computer faster, and it has a less impact on your data plan if you have one. This can be important if you're, important cost thing. So in general, though, if your overall compression algorithm, that's something you can decide at the user end, though, which version of the file you want served to you. But in general, if we can get the highest quality content compressed and delivered to you, at a smaller package, then that basically means that saves money on our end and our servers. That's huge. It saves money for the consumers if they've got a data plan. It's pretty good. The cost for doing compression, of course, is that your computer has to do a bit more work to do it. And somebody else, of course, has to think of a good compression algorithm. In fact, there's an entire series based off a compression algorithm, Silicon Valley on HBO. That was the entire thing is based off the fact that you've got this theoretically amazing compression algorithm. So now these are lossy video algorithms. They can deal, basically the idea here is that it balances the amount of jankiness that is in a video stream to the fact that our eyes can't really detect a bad output. But there's also one other type of, and that's lossy, meaning some data is lost in the compression, but that's a trade-off. And that's fine for media that we consume, like audio media and visual media. But if it's text, that's not so good. So there's another type of compression we can do, which is lossless. And so in terms of audio, let's go ahead and render this one more time. This time I'm going to go and use what's called FLAC, which stands for Free Audio Lossless codec. I'm going to go and basically it can choose what compression level I want. The idea here is that the more compression it does, the longer it takes. And this is something like a zip file. So I'm going to go ahead and compress it as much as possible. Let's see. And I called it good MP3, even though it's a FLAC. So, and it's 1.3 megabytes versus 1.2 megabytes. So it's about half. It's less than half the size. And no data has been lost. It's the same WAV file. It's just this thing has been compressed. So that's obviously very valuable if you need to save like the production level values of something, because if you're working in video and video files, those things are going to take up a lot of space. So compression algorithms, they make the world go round in some way, in some ways. The less data, the less data consumed, that means less energy consumed. So compression is very important. So today's topic is going to be talking about Huffman encoding, which is a type of lossless compression, meaning that we don't lose any data. Specifically, this is a type of lossless compression that deals with that's made for text. Because if you think about it, you can't, if you're compressing text, you don't want to throw out any of the data. Like, think about how a message would be, how one message could read if we accidentally threw out the word not in the middle of the message you sent, right? You can think of all the horrible shenanigans that would cause. Like if your significant other texted you, hey, I'm feeling sick today, and I texted back, oh, that's not good, and the compression algorithm threw out the not. Oh, that would so very important that something says that some messages are lossless, right? Now when we develop things like ASCII, we don't really care about compression, and ASCII is kind of the basis for the way text is encoded. Text is encoded in a lot of ways. The current text encoding that is used predominantly in the internet is UTF-8, which is, again, Tom Scott has a wonderful video about this video that you should totally watch. There's a wonderful video about this topic, which you should totally watch. And the entire point is that it is a format for encoding Unicode, which is the way, you see, the problem with ASCII was that here's the ASCII table. It takes 7 bits, okay, for basically all the basic characters that you would need in English plain text and for basic kind of transmission that we needed. So we had all these control characters, a null, a start of heading, a start of text, end of transmission. These are kind of older things that you would need for when computers would communicate with each other. A specific control code for when you hit the backspace key, right? That's got an encoding. The bell for literally making the computer beep at you. /n, you're familiar with this, and /t, those are, new line and horizontal tab. That encodes into the computer this sequence to produce a tab or a new line. And we keep using this format because of backwards compatibility. And then we've got all these symbols, right? We've got all the symbols that you'll recognize on a US keyboard, right? Space, your symbols, your capital letters, your lowercase letters, and then there's just some other stuff as well. And the idea here is that we've got all these things encoded in 7 bits, but everything is done in 8 bytes, sorry, a byte, which is 8 bits. So that leaves 128 characters left over for your language, for whatever language you're using. And that led to a lot of issues with, like, okay, but this was written by a German on a German computer, and now the encoding's all weird and different on my computer because it's an IBM computer made in the US, and those characters don't look at all right on my computer. But there was another bigger problem with that, with the fact, right? There's any guesses as to what that is? What's the problem with ASCII as with universal adoption of it? Yes.
I believe applies to like the English language.
Yep. Latin-based languages or Latin-based characters, right? So, like for instance, I'm going to talk about this mildly because I only mildly know about it. But what about kanji? Kanji, which are Japanese, which is one of the Japanese syllable, one of three different sets of typographical characters that are used by Japanese people based on Chinese characters. These are there are about, I think, like 2,000 of them in official use, and then there's like more of those. So like children use learn 1,026 first kanji characters in elementary school from 1st to 6th grade. So you know, that's a lot. That's a lot to write. How do you? But they deserve, you know, everybody deserves to be on the internet and communicate with each other and use computers. So that's why we use Unicode, which says, okay, we need to be able to just create. We have tons of coding space. Let's see, they have tons of space for characters. Yeah. And you can do random ligatures, which is important in Arabic or this word I'm not even familiar with, which is based on ancient Sanskrit used in the Indian subcontinent. So, but you can do arbitrary ligatures, which is extremely important in certain languages. You can create, and that's the reason why you can also see why you can use certain characters. Pretty much every programming language can work in UTF-8 now. It used to be a huge issue still, even like 10 years ago, I feel, if I'm remembering correctly. But in UTF-8, what that is that's just basically a way of like encoding it to be a bit more efficient when in transmission. But the thing with ASCII is that as far as compression goes, it's a rubbish format. Because every single character has the same kind of it takes up the exact same amount of space, a byte, right? And E is denoted by the sequence 11000101, and a Z is denoted by the sequence 1111010, right? With a leading zero because it's a byte, so you'd have a leading zero in there. Okay. But so everything takes the amount of the same amount of space, every single character group you make. But the idea is, what if we change that? What if we basically change that so that we take advantage of the fact that some things are more common, some things reoccur. For instance, let's take a look at a visual example for blue marble. Okay, one of the most famous, not blue marble, blue marble. The blue marble, one of the most famous pictures of all time, picture of Earth from space. There's a lot of black in there. So we can encode that. So the idea here is that we can encode that with a very simple sequence, a very short sequence. And tell the computer, if you see this short sequence, but if we see other, then we do this. And then this orange, brownish, greenish stuff, that will give that a longer sequence. So the sequences of colors will have a variable length to them. Similarly with English, what we're going to do is we're going to have the more common characters have a shorter length of a shorter bit sequence, okay? And we're going to have the longer characters, sorry, the less often characters like Z and J, they'll have a much longer sequence, okay? Now, here's where it kind of, here's the catch, right? We can't just make a encoding, a one-size-fits-all encoding, right? This picture is made up of a lot of black, but if we're taking pictures of people or of
buildings, it's completely variable what the colors are going to be. It's going to run the complete gamut. Similarly, you might think, okay, we'll just have a you know, with text, we will base that off of like the most common character is E. So obviously E will always have the least number of bits, except there are people who have no time, who have too much time on their hands, and they write novels like Gatsby, which is one of those books that people write as a challenge. It is a book written in 1939 by Ernest Vincent Wright that does not include any words that contain the letter E, because again, 1939, no internet, I guess, you know. No internet, no TV, no video games. The idea here is revolves around the dying fictional city of Branton Hills, which is revitalized as the result of an effort of protagonist John Gatsby and the youth organized. Though vanished, depublished, and little notice at the time, the book has become favorable to fans of constrained writing, which is actually a thing. It is cool to do a challenge like it. I joke about, about him having too much time, but honestly, taking a challenge like, hey, I want to write this thing without using the letter E, or hey, I want to write a book, but only use the 1,000 most common words, like Randall Munroe did in his Thing Explainer book. It's an interesting challenge. Limitation breeds creativity. Okay. Part of the reason we emphasize, even though you know how to use linked lists, we emphasize knowing how to use the stack or the queue, because having a limited operation set makes you think in different ways, makes you solve problems. So as much as I joke about it being about this being a waste of time, it's really not. And I wouldn't be talking about it otherwise, because it's a great example of you can't make assumptions about the text you are encoding. So the key is that we have to basically make an encryption scheme for every single text we write. And what we're going to do is that we are going to, and the way it basically works in practice is that if you encrypt something, like in a zip file, what you're doing is that you're also you're sending basically the instructions of, this is how I compressed it, and this is the key. This is the compression key. So this is what you want to unpack. So Huffman encoding, or Huffman coding. Information is an optimal prefix code for lossless data compression, developed by David A. Huffman when he was a Doctor of Science student at MIT and published in 1952. And it is like a bit painful to try to figure out, but hey, it works. So the idea here is, let's go ahead and encoding. There was one that I used to see that basically would grab the latest headline and Huffman encode it. So let's go and say, but let's go ahead and like figure out, let's go ahead and just like encode an arbitrary DNA sequence. Like, hey, random DNA sequence of, that sounds good. So DNA sequences, they have what, like 4 characters, right? I took a PhD level bioinformatics class. I should know this. Seriously, it was all about like learning how to talk to biologists and how to read papers that talked about proteins. Like I can read those papers now. It's just have to like look up every other term sometimes. Okay, so okay, random DNA sequence. Let's go with length 10. Submit. Okay. There we go. Here is, and here I'll put it on Notepad so we can actually read it. Okay, so here's a random DNA sequence, and let's say we wanted to encode that using Huffman encoding. Now, the premise here is, though, that this would be a terrible example for Huffman encoding because it would actually be bigger because the instructions on how to decode it would be bigger than the sequence. But for academic purposes, this is great. So we've got, what we do first is we do a frequency count. We count how often each character appears. So G appears once. Okay, C appears 3 times. A appears twice. And T appears 3 times. So the idea here is what we're going to do is that we are going to create a priority queue. A hash, which is built off using a heap, if you remember from the videos. But we build up a priority queue, which is a queue that reorders itself, that it basically lets people, lets objects in it cut in line based on how important they are. Okay, and we're going to say the lower your frequency, the more important you are. That's not true, but what it is the lower you are, then you need to be first in line. So G will be first in line. A will be next. C and T. And we'll do this off of something else that's a bit more, less contrived in a bit. Okay. So what we've got here is that we then start, yes. Excellent. Okay, that makes it even better because then I don't have to worry about arbitrarily breaking ties. Thank you so much. I was just testing you. All right. So what we do here is that we dequeue the first 2 things on the. So the first thing we need to do is figure out our encoding scheme. So we do this by doing the frequency count, which we just did. Was a team effort. And then what we do is we dequeue the first 2 things. So the first thing goes on the left, the second thing goes on the right. And we basically start building a tree. So G and A, they come together and they have a combined frequency of 3. Make sense? They have a combined frequency of 3. So they got dequeued. And now what we're going to do is that we are going to put them back into the queue. With so we have G and A together, okay, that has a combined frequency of 3. And this is where most people mess up in encoding. It's a priority queue, meaning that it reshuffles. So that means that basically the 3T, the G and the GA, I'm going to arbitrarily break ties by saying, hey, this is GA, so it's going to go over here after the thing with only 1 item in it, right? But the point being is that it cuts in front of 4 because it's less than 4. That's the more important thing. Okay. Now what we do is that we repeat. We dequeue the T and the GA, and we make a new root node over here, which has a combined weight of both of those, which is 6. We put the T on the left and this guy on the right. Make sense? Okay, this root on the right. Okay, and now we add this back into the priority queue. Okay, so the idea here now is that we will, so we have TGA over here. We have 4 and 6. And so now what we do is we dequeue again. C goes on the left. This giant one goes on the right. And we get 10, which is all the characters, right? And then we put it back in. And then there's only, and now there's only one thing left in here. So we're done. CT, GA, right? So let me go ahead and 1 second, make it a bit cleaner to, I said a bit cleaner to see, not less clean. Okay. So now that we've got this, now that we've got this tree, we can use it to determine the encoding for all the characters, and it's fairly simple. You put up, I mean, I say it's fairly simple, but I'm gonna look it up just because I'm because I'm paranoid. Okay. A is yes. A is 0, 1, 0. Okay. Yep. So that means that we put zeros on the left edges and ones on the right edges. I always have to look it up because it's been a while since I did this. But I mean, as long as I'm consistent. And the idea here is that we can now encode this sequence. Okay. And the encoding is as follows. A C is a 0. If I see a 0, sorry, C's get translated to zeros, T's get translated to 1 zeros, G's get translated to 1 1 0, and A's get translated to 1 1 1. So overall, this is going to become 1 1 0 0 0 1 1 1 0 1 1 1 0, and then 1 0 1 0 1 0. Okay, now how in the world do I decode and how in the world do I decode this? This is much less than 8 bytes, but sorry, 10 bytes, by the way. So it does compress quite well. But how in the world do I decode this, right? How do I tell the difference between a 0 and a 0 and a 1 0? And the answer is I go by left to right to decode it. I have to basically follow this tree. So what I'm going to do, so if I erase this over here, so let's go ahead and read this binary sequence that I've horribly drawn out over here. So I've got 1, so I've got 1 1 0, so and I got to an end node, so that means a leaf, that means it's a G. So I've done this bit. Now I see a 0 leads me to, and so now that I got to an end node, I'd start at the beginning again, at the top of the tree. So now I did 1 1 0. Now that got me to an end node. Now I start at the root again. 0, go to left, that's a C. So 0, that's a C. 1 1 1, that's 1 1 1, that's a T. Sorry, that's 1 1's an A. A 0, that's a C. And then 1 1 1, that's an A. So I go back up now that I'm done. A 0, that's a C. And now I've got 3 T's on the end, which will basically be done by going 1 0 1 0 and 1 0. Make sense? It takes a couple of times trying to do it yourself. And it's broken up into 2 parts. Typically, the way I do this on the exam is that I give you and again, I'm not going to do this on the exam this time around because COVID. I'm not going to probably start reintroducing this into exams until back in but again, I didn't want to deny you the education of this. And besides, I got to show off my music. So the idea here is that if I test you on this, generally it would be tested like basically I'd say, hey, given this, construct a tree. And then like decode a word like apple or banana from the tree. You know, like tell me what apple or banana translates to, or I'll give you for what it should have been and what should translate to apple or banana. So, or some other kind of fruit. So, but Huffman but compression, as you can see, this is much smaller than the 80 bits this would normally take to compress something. You know, and compressing text is compressing in general and coming up with a great compression algorithm is tough work, but it's valuable work. All right, being able to transmit your videos at a higher resolution in a lower and higher fidelity for a lower cost to yourself is huge. So there's a lot of different formats out there. I think what VP9, I think, is a royalty-free video coding format. That's Google's one that competes with the HVEC or HVEVC. VP9 is mainly used on YouTube. Another one that's big is AV1, which is developed as a successor for VP9, and it is amazingly so. Here's the thing, AV1 like could get these like giant files down to like small, like 2 GB sizes, you know, things that would normally be 10 GB, but it was still so cutting edge that like you know, you'd need like a good strong GPU to decode it and run it at a watchable frame rate. I mean, now that GPUs have, you know, that also like it depends. Do GPUs or CPUs have a dedicated, you know, circuitry in them, dedicated things in them to help decode these special instructions faster? So it becomes a big thing based on this. 50% smaller than X265, which is one of the big ones that's still big and very active in the piracy scene. That one is still there, big. And this one's good, but again, it takes more. This high efficiency video one, it's used by 43% of video developers. So there's a lot that goes into like compression and making sure that video can be compressed, and it's not necessarily lossless, right? It's all about balancing. So anyway, that's all what I've got for today. I hope you enjoyed this 40-minute diatribe on my part. So please try to get your exam corrections turned in by Friday. I don't need to have them seen by Friday, but like have them turned in by Friday, because I just don't want this to. And the reason I have that quote unquote deadline is because I don't want this to go on forever, you know. I don't want to have to deal with this again at the end of the semester with people scurrying for points. But if stuff comes up and you need it and you need an extension, just email me. Yes. What? No, is if you've got a score in there already, it would be good for you to upload them so it doesn't accidentally get erased though. Or like if it accidentally gets erased, there's a paper trail. Is more the point. All right. Now, so if you've got demos, corrections, questions, comments, concerns, criticisms, existential crises, let me know.
Professor,
All right, let me